Finally, now we're gonna show that the orthogonal group of a regular quadratic space is generated by symmetries. Actually, a stronger statement holds, so every element of the orthogonal group can be written as a product of at most n symmetries, where n is the dimension of the quadratic space. But in this video, we're just gonna prove the weaker version. So let sigma be an OV. We wanna show that sigma is gonna be a product of symmetries. Here we want to use a result from before. Remember, in the previous video, we claimed that if we have two vectors, x and y, such that they have the same quote-unquote norm, and the norm is non-zero, then there must exist a product of symmetries sending x to y and vice versa. We'll now prove this proposition using induction on the dimension of V. So let's look at the case when the dimension of V is 1. So V is spanned by a single vector x. And note here that the norm of x must not be 0. Why is that? Because V is regular, and remember that means that the discriminant of V is non-zero. The discriminant of V, the matrix of V, just has one entry, right? It's just the Q of x, so Qx must be non-zero. Then in that case, observe that if this sigma is an isometry, then by definition of isometry, sigma x and x must have the same norm. So by the proposition we proved in the previous video that we mentioned here, we see that then there must be a product of symmetries mapping x to sigma x. Thus, sigma x is equal to psi x, where psi is a product of symmetry. But then this means that sigma must be equal to psi because the vector space V is spanned by x. So the image of x determines the image of every vector under this. So we are done because now sigma is equal to psi, which is a product of symmetries. Now let's consider the case when the dimension of V is greater than 1. We suppose by induction that the proposition is true for all regular spaces of dimension strictly less than n. To be able to use induction, we'll pick out a vector of V with norm not equals to 0, and then we'll have the following decomposition. Because this space must be a regular space because its discriminant is non-zero. And why can we pick out a vector V with non-zero norm? Because if all vectors of V are gonna be of zero norm, then in particular, so must its orthogonal basis, and so the discriminant of V must be 0, contradicting the fact that V is regular. So now that we have this decomposition, we pick out this x, we can try to repeat the argument before. Now sigma, again, remember sigma is an isometry. Now sigma x must have the same norm then as x by definition of isometry. So here we have two choices how to proceed. We might proceed as before and we say because sigma x is equal to x, so there must exist psi, which is a product of symmetries taking x to sigma x, i.e. we have that psi x is equal to sigma x. But now the situation is a bit different from before, because this does not mean that psi is gonna equal to sigma on the whole of V. They only agree at one point. They only agree on x. And we know they only agree on the span of x. And we are also not using any induction hypothesis. You might say, let's look at sigma restricted to U by induction hypothesis. It's gonna be a product of symmetries. But this does not work because sigma restricted to U is not necessarily an isometry onto U, because sigma might not map U into U. So instead we will exploit this fact in a different way. We claim that then there must be psi a product of symmetry sending sigma x to x. In other words, psi of sigma x is equal to x. Why is this a better view? Well, because this means that psi sigma fixes the span of x. Right? So the span of x is an eigenspace of psi sigma. Now if it fixes, or in other words, psi sigma restricts to an isometry of this span of x. Now that also means that psi sigma must also restricts to an isometry of U. Psi sigma must map U into U. Why is that? Because as an isometry, it must preserves orthogonality, but U is orthogonal to the span of x. So if psi sigma preserves the span of x, it must also maps U into U. So psi sigma restricted to U is an isometry of U, and thus by the induction hypothesis we see then that it must be a product of symmetries. Each of these symmetry extends uniquely to a symmetry on the whole of V, so psi sigma itself is a product of these symmetries. And so sigma itself must be a product of symmetries as desired. Thus we have shown that every isometry of a regular quadratic space is a product of symmetries.